So, hello everybody. My name is Dr. Alex Ivanenko. I'm the co-founder and CEO of HyPoint. I would like to say thank you very much that you found time to speak with us today, and we will be happy to share with you our new collaboration with BASF, and where is the main aim of that collaboration to create, kind of say, game-changing membrane electrode assembly, which is a core technology and core part of fuel cell. And that collaboration can bring us to the next level of specific power, not less than 3 kilowatts per kilogram. So today, with me, our co-founder team, who is responsible for that collaboration. So let me introduce you to Rhonda Stout. She's our chief MIA engineer, and she's responsible for in general for that program. So Dr. Brian Benishevich, who is the inventor of high temperature membrane, and Brian, chief science in the company at HyPoint, and Sergei Shubinkov, who spent more than 15 years in fuel cell research and development. And Sergei, at the same time, he's our R&D director. So all that team is responsible for and involved in the process with BASF collaboration to create a new membrane electrode assembly. So I think before we start, I gotta say, I think it will be great if Sergei Shubinkov and team will provide you general information about what's the aim of that agreement, and what's the parameter we are going to achieve, what's the performance we expect, and after that we will be ready to answer all your questions. Does it work for you? I hope yes. Sergei, your turn.
Okay, thank you everybody for visiting us. I would like to say you that we are very much excited with this meeting with you, and would like to describe you briefly our goals, our R&D goals regarding developing new membrane electrode assemblies with in partnership with BASF. Let's start. Let me explain first what's the difference between high temperature PEM fuel cells and low temperature PEM fuel cells. Typically, most of developers build their system on low temperature PEM fuel cells, which operates at low temperatures, about 60, 70 degrees Celsius. Our technology, our high temperature PEM fuel cell, is the pretty new technology, which operates at a relatively high temperature, about 160, 180 degrees Celsius. But this is not the only difference between these two technologies. And I would like to emphasize, you see here the table of features and comparison of LTPM and HTPM, but I would like to pay your attention to three main features. First of all, high temperature PEM fuel cell provides a broader temperature range, and this is very important from the point of view of cooling, because high temperature allow to simplify heat rejection, and wider temperature range allow us to implement air cooling instead of typically used liquid cooling system, and this dramatically reduces weight of the system. That is very important for air applications. Second, our fuel cell does not use water in any form, and no absence of water management makes our fuel cell much more reliable, which is also important for air applications. You may see on the right hand of this slide diagram representing how our fuel cell operate in emergency case. For example, in the case of overheating and overcurrent overloading, our fuel cell can operate at least 30 minutes, at least, maybe more. We didn't test it yet, but at least 30 minutes, allowing crew to safely land the aircraft. And after these 30 minutes, if you continue normal operation, it will provide you power. And Also, very important thing that potentially fuel cells, HPM fuel cells, are much cheaper in serial production. Let me explain that these features of fuel cell, of our HTPM fuel cell, allowing us to build a significantly lighter and simpler and more reliable system that could be implemented for air transportation. And our invention, turbo air-cooled fuel cell system based on HTPM, now we developing this system in order to achieve 2 kilogram per kilowatt of specific power for the whole system on a system level, not on a stack or individual fuel cell, for the whole system level, which is unbelievable for all existing fuel cells. But our aim is to improve at least by 2 times, and this new program, R&D program with BASF, should allow us to do this. And I would like to explain you how we're going to reach these absolutely fantastic figures. I would like to ask Brian. Brian, if you can, could you explain us what the improvement was made? How was the evolution of the core of HTPM fuel cell, of the membranes, which is in the basis of any fuel cell technology? Brian?
Yep. Well, good morning to everyone, if it's in fact morning where you are. Yeah, there's been a lot of work going on over the last 15 years in high temperature PEM development, not necessarily for aviation, but still we're building on that platform. And you can see here, particularly in the recent few years, there's been significant improvements in almost every aspect of the high temperature membrane itself. And so we've seen increases in power when tested under similar conditions. So this is a real apples to apples comparison, and maybe not even the best we can do, but it shows the apples to apples type comparison, and significant increase in the power we can expect from the high temperature PBI membrane. The thickness has improved. It's gotten thinner, which helps volume and weight. And simultaneously, we've seen increases in durability, particularly very long-term durability and a very low degradation rate at the same time. And then a few years ago, when, once you get to 2 and 3 year lifetimes, people say, well, what is the failure mode? And there was a lot of work done to identify it, and particularly in one of compression creep. And we've even improved that by a factor of 5 over the last several years. So we think really with these new developments, our partnership with BASF, we can now take all of these developments and really tailor this for the aviation market. So I can answer questions later if we want to get to some technical details.
Okay, thank you, Brian. But let me explain that yes, the membrane is the core technology in any fuel cell, in HTPM fuel cell also, but we are going to develop absolutely new membrane electrode assembly which generates electric power, and the program we have started already should allow us to increase significantly power output. Let me explain our goal. So at the moment, with the current technology, I mean with the current membrane, we are able to achieve significant power density, and as I explained, this power density is sufficient to provide 2 kilogram per kilowatt per kilogram of specific power. But in 3 coming years, 3 years will be 3.5 years, we are going gradually increase this power density by 60%. And in addition to this, we are going to increase durability of the system, reliability, and significantly reduce cost of the fuel cell, of individual fuel cells. All these improvements should allow us to provide at least 3 kilowatt of per kilogram of specific power on the system level, and we hope to get more, up to 4. What is our approach? How are we going to reach these fantastic results? First of all, based on, as I said, new membrane, we're going to develop a new specific catalyst recipe, which provides high efficiency and higher durability at higher temperature, operational temperatures, which we are going to achieve. And in addition to this, this new recipe would allow us to reduce platinum load and cost. The thinner GDL, along with the thinner catalyst layers, should allow us to significantly increase higher performance power output of individual fuel cells. As I said, new catalyst should provide high durability. We are going to increase temperature. We are going to provide at least 15,000 of operation, and a new catalyst is the key for these figures. Should provide this improvement, I mean durability. Thinner GDL, so layers, catalytic layers, catalyst layers, and GDL's electrodes together should provide us 60% improvement in performance. And higher temperature, operational temperature, provide not only higher output of individual fuel cells, but also should increase efficiency on the system level, which is very important because we consider all figures on a system level. Let me explain that MEA development is not the only program. We are also focusing on a number of improvements in our system. We develop our unique bipolar plates. We develop materials for them, design for them, coatings for bipolar plates. This is also very big program which should improve performance and durability of the system. We are developing new architecture for turbo air-cooled fuel cell system, which is also innovative and should allow us to build the system for high altitude operations. Now our system is considering for 6,000-7,000 meters over sea level, but next generation will provide 11-12 kilometers. And together with the new cooling system, we will be to provide megawatt class systems. We will be able to provide high altitude operations and 4 kilowatt per kilogram at system level. Where we are going to reach to achieve all these results. Let me present to you our R&D and assembly facilities in the UK, in the Discovery Park, which is near the city Canterbury. This facility was built, developed, constructed by Pfizer, a well-known famous company, and now we have rented 2 spaces and are going to rent additional spaces. And you may see these pictures. We have enough space not only for developing for our R&D program, but also for assembling and for pilot production. We have also very good staff. Not only we 4 presenting here our project, but also very high qualified engineers and scientists behind us. And now we are confident that all our R&D goals will be achieved with help of our brilliant team. Thank you.
Yeah, so I think that is what we have. So once, just to emphasize what we are going to achieve here, that new membrane electrode assembly with new membrane of BASF, we are going to build the system which directly will, bring us to the next level of specific power. So, and seems that megawatt class power level specifically for not only for eVTOL, but it's also very, very important for fixed wing plane, narrow body fixed wing planes, because it's like a jets or turbine, turboprops. It's very, very important to have higher specific power and higher specific volume. So, and that's a minimum level that we are going to achieve during that calibration, 3 kilowatts per kilogram. It is exactly what aircraft designers are looking for. So once again, thank you very much for your attention. Rhonda, if you would like to add something here, it will be great.
Oh, so this is an excellent team that has the ability to really bring the high temperature PEM technology to a real commercial product. And it's exciting to be working on this. I've been working with BASF for over 15 years, and with a market that really needs a product and a technology that can deliver the kind of performance that we're talking about, it's a perfect marriage for success. So, thanks.
All right.
Okay. Yeah, ready to answer on your questions.
All right, I will go ahead and open up microphones. So who would like to go first? Any questions from Dave, Ilan, Ken, or Mike?
At what point, this is Dave, that helps.
Yep, we got you, Dave.
Pardon?
We hear you.
Do you have target customers in mind for the technology and the cells? And are you working with them to shape how you develop the cell?
Yes, exactly. So so we right now see a few market segments inside the air transportation market. And when we started, so the first request from our customers like Piasecki was we have to deliver them at system level not less than 2 kilowatts per kilogram. And for small fixed wing planes, it also works well. But for bigger aircrafts like narrow bodies, megawatt class fuel cells, seems that 2 kilowatts per kilogram is not enough at system level. So that is why we started to think about how we can achieve that level so in a short period of time. And you know that we bet on high temperature membrane from the beginning, and we so discussed that question with Brian. And evolution of HTPM membrane seems that it can bring us to higher level. So 4 kilowatts per kilogram, it is exactly what we received in our mathematical models. But actually, we will achieve 3 kilowatts per kilogram, let's say, for megawatt class fuel cells, specifically for big aircrafts, narrow body aircrafts, 90 seats inside. It would work too. So especially if we are talking about high altitude flights, because HTPM has a lot of benefits here. So we exactly understand what is our market segment where we address that specific power, because this is requirements for big aircrafts, narrow body aircraft makers like Airbus, like Embraer, and etc. But of course, that technology, 3 kilowatts per kilogram, it will be better to integrate in any eVTOL.
And where on the aircraft does the fuel cell sit?
So it depends on, this is a good question actually, and depends on customer requirements. So for instance, you know that we are working with Piasecki, and last week we just finished our 2 weeks collect. Can you hear me?
Yes.
So, and 2 weeks ago, last week, we just finished our 2 weeks collocation meeting with Piasecki when their engineering team meet with our engineering team. We spent about 2 weeks on that to define exact very specific layout of our fuel cell inside their aircraft. So it depends. So our system is modular, and you can, how to say modular, I mean that we built a single power module, and if you, for instance, have to achieve 2 kilowatts per 200 kilowatts, you just need to arrange together 10 single 20 kilowatt single power modules together. So that's main idea. System is modular, and how we will integrate the system in specific aircraft is a question of designing team, and it's a question of discussion with our customers.
And what could go wrong if I'm a passenger on a plane?
Oh, that's really good question. Sergey, can you please open the last slide, and I kindly ask Ron to explain that slide, our testings regarding how HTPM is reliable in comparison with low temp.
Is this Dave that I'm talking to? Dave, so
Yes.
our experience with high temperature PEM and the testing that we've run to date, if there were things such as an emergency and where we needed to go to a higher power setting to be able to land the aircraft, the graph that's shown here shows that we could go to a much higher power for a long period of time, a half an hour at least, to enable the aircraft to land safely. And you can even see that even at that high power density, the cell recovered once we were under normal operations. So it's really important evidence to show the robustness of the technology. We believe that low temperature PEM, on the other hand, operating with its water management issues, would not be able to achieve. We haven't tested it ourselves, but it would be very difficult for a cell to spend that time, because when you have higher current density, you're creating more water and you have higher risk for failures. And so we see that high temp PEM is very robust and able to handle these kind of operating conditions that would allow for a safe landing.
Yeah, thank you. And I would like to add that we also following a modular approach, as Alex explained you, and this approach is not just a phrase. Our architecture of our system is how to say developed in the way when failure of one fuel cell mode in any failure in any possibilities that happen during the flight
that's a good
will
point.
not significantly affect on the system level.
Yeah, so one of the requirements for fuel cell systems in aviation is that there are redundant systems, and it's not just for the fuel cell, but redundancy is a key requirement across the entire aircraft. And so that's how we are designing our system to have multiple redundancy points to make sure that there's never a single failure.
And does the technology have application in other industries?
Oh, why,
Yes.
of course.
Yes, we in the beginning of next year, so I think in January or February, we will bring to the market 20 kilowatt single power module based on high temperature membrane. And this is like a platform solution. Why we started from air transportation market, because we can see that we can bring a lot of benefits in very quickly to the market. But actually, this is a platforming solution, and that single power module might be integrated in any industries, like a marine application, heavy duty trucks, and station applications, or any, because this is a platforming solution. And by we started to work with air transportation market, as I said earlier, so it is we can bring benefits very quickly, because no one right now doesn't have any solution for air transportation market, and actually we don't have any real competition. But if we will, we're gonna say like a startup company, we bring the technology to the heavy-duty truck market, it will be complicated to convince, let's say, big guys to work with HyPoint. But when we will build a product, so this is one of our aim, to develop licensing agreement with heavy-duty trucks manufacturers, with marine market, in telecom industry, and etc. Because HTPM membrane, there are a lot of benefits you can take from that technology. Like one of it, it's truly climate independent. It can be operated at any weather condition, -60 to +60. So it's absolutely tolerant to any type of hydrogen, I would say, and any grade of hydrogen. So it can contain up to several % of carbon monoxide, and etc., etc. A lot of benefits here. But our product, 20 kilowatt single power module, can be like a solution for a wide range of applications. Of course, that is one of our aim, but it will not be directly, promoted by HyPoint. We are going to develop the network of our partners, provide them licensing for that product, and they can build balance of plant based on their specific requirements for specific market segment.
So that kind of leads to my next question. Are you in the process of, or will you need to develop your entire own ecosystem of people who are trained and certified to operate the fuel cell, to maintain the fuel cell, to repair the fuel cell? Since it's a proprietary technology and it's new, just from my own civilian, if you will, passenger experience, there's a guy who comes out and goes up to the Rolls-Royce engine and makes sure everything is tight. And there's another guy who will replace a part.
That's absolutely good question. Absolutely good question. And you should understand, yes, so it's completely different in comparison with low temp membrane, which is commonly used right now in the market. But in in the customer point of view, there is no big differences in operation and maintenance and etc. So Rhonda, you have a lot of experience, right? So you were at Plug Power and you build the system for household use, right? And
right.
Your job.
Yeah. So what I would say in response to concerns about maintainability of the systems, we're specifically designing our system to fit within the construct of how aircraft operators have to go through their pre-flight checks, their maintenance routines. So everything will be trainable and fit within that current structure. And so like with our modular design, and our monitoring systems, we'll be able to look at a stack, understand how it's behaving, a stack or a single power module, and there will be notifications that can be sent if there are, if there's anything that might be of concern. There'll be cockpit monitoring of the system, as well as regular maintenance intervals, and that's just typical of what goes on in a aviation environment. And as far as robustness, I worked on a high temp PEM stationary system, and some of the data that we're talking about here, about 20,000 hours achieved, is what we experienced 10 and 15 years ago in our lab environment, and Brian can attest to that as well. So it's a very robust technology, and it's something that design will make it maintainable by a regular aircraft personnel.
And have you looked at a comparison between your system's overall long-term operating costs and the other, let's compare it, say, to the battery systems that are currently being developed for electric aircraft? How does your system compare?
So we did, for instance, comparison for different power sources. We estimate total cost of ownership for different flying platforms, and especially if we are talking about eVTOLs. So in comparison with standard gasoline or diesel, so we can achieve up to 50% reduction of total cost of ownership. If we are talking about ideal battery, like 5,000 cycles, recharging and etc., which is not completely impossible to do so. So we will be cheaper in comparison with them, about 10%. But for real batteries right now, we can achieve 25% reduction in comparison with them. So if we're talking about standard gasoline, it's a 50% reduction in comparison with and based on total cost of ownership. So and 25% reduction in comparison with lithium batteries.
And with an array of these, what is, whether in distance or time, the operating range? How far can you go on, sorry for using the wrong term, a single charge, but can you go on
single charge? Why not? So yeah,
okay.
Single charge. It's absolutely correct. Correct. So single charge means that you charge the storage, and that is important because fuel cells just provide you power, so they don't have any, how to say, capacity and energy. All energy in storage in hydrogen storage. So it might be liquid hydrogen, it might be gaseous, compressed hydrogen, and depends on that. And depends on what the customer wants. Because, for instance, for air taxis, you can define the flight time, but of course you can fly 3-4 hours, depends on, or 10 minutes, depends on your business model. So let's business model, for instance, like an air taxi sharing, right? So you have to execute very how to say, short time flight, just like a taxi, like 3-5 minutes. Right, so you can fill up some cylinders and you can cover about all day of operation. But if, for instance, operating like a medical service, you have to fly about 3 hours on just one charge, right? So just charge of hydrogen, and hydrogen can bring not only how to say, long flight time, but they also can bring you efficiency of your operational business model. Because you don't need to waste your time on waiting when the lithium batteries will be charged. I'm living in Palo Alto using Toyota Mirai, and I just need to spend about 3-5 minutes to fill up my car until how to say, until maximum. So it's very easy, and I can drive next 250 miles on the car. So, but for lithium batteries, and at the same time in the UK we have a manufacturer site. We just purchase a fully electric car because no infrastructure right now in UK. So, and just to add 30% of batteries, I have to charge about 6 hours all night, just to add 30% of capacity of the batteries. So full, it means that if it's very important to very, how to say, high intensive flight, so you don't have any chance to use other sources, only hydrogen will be an answer for you. If you would like to fly longer, long distance, hydrogen is the answer.
And
but
so
if, for instance, it's a for private use, you have enough time just to fly from home to your office and back in several hours, perhaps that technology, the standard lithium batteries technology, will work for you. The same as for Tesla. So that is why I actually don't believe right now in hydrogen for private use cars. So like Toyota Mirai, I'm using Toyota Mirai because what kind of car should I use, right? We have fuel cell makers, but actually Tesla or other manufacturer fully lithium batteries will cover all my needs, just to bring me to save way, purchase the goods and back 10 miles maximum a day, and that's it. So I don't need to really use hydrogen for that.
So will you need to build a network of hydrogen stations across the state, across the country? How will operators refuel their cells?
So this is also a good question, and actually it depends again what is the business model. So if we are talking about just flights in airports, it's not a big deal to install that additional refilling stations in airport, because right now airports has a lot of all necessary certificates and permissions from authorities to use that type of hydrogen, any dangerous gases. If we are talking about eVTOL market, so of course we have to develop and think about infrastructure. And I know that there are a lot of companies right now is developing different types of concepts of green hydrogen. And actually, this is one of the points which we usually discuss internally with our hydrogen eVTOL council. So this is a very, very important question, of course, to develop infrastructure, and we have to define the places and etc. But this is a topic which should be covered by other companies who's involved in that question specifically.
So do I understand it correctly? It's to use an example, it's Shell Oil, which has refineries and places where they drill the oil, and the consumer gets it at a corner gas station, or in this case at an airport. If it's let's say an air taxi operator, is it going to be, when you say others, there's going to be this wholesale retail network where people can get it to get their cells recharged?
Sorry, I'm not sure that I completely understand your question.
So Dave, I think that so we're not recharging the cells, which is our responsibility, is the fuel cell stacks. The fuel is put into hydrogen tanks, either on board the vehicle, and so we're not engaged in the refilling and the stations to refill. Those are those are the companies, our customers, that's what they're dealing with, and generally the hydrogen storage is on their side of the responsibility. We're supplying the power for the powertrain through our fuel cell module, but the fuel goes into a tank that gets fed to the fuel cell system.
Okay, so you provide the power cell, the engine, so to speak, and the
gas goes in the tank, and the tank isn't on our side.
Right. Okay.
Nor is the station to provide that. So, but it's definitely all of the customers that we're engaged with, they have active programs that are looking at infrastructures and how to enable it at airports and wherever they're going to be flying out of.
And I don't want to dominate the conversation, so just one more question. Where will your pilot site be operational first?
Where's our first site, Alex?
So you mean eVTOL or fixing planes?
Your aircraft, I'm not pronouncing it right, the Piasecki.
Piasecki, yeah. So actually, we, as Rhonda said, so if you, let's imagine power plant, right? So it's four main components: propeller, motor, fuel cell, and hydrogen storage. So we are responsible for that specific everything between motor and hydrogen storage. So this is what HyPoint usually do, and that's we are focusing on specifically that company. Regarding where it will be operated and etc. Of course, the question you have to address our. So of course I know that, but I don't think that is I'm the right person who should answer on that question specifically where the first aircraft should be operated and etc. So I think you have to address that question to eVTOL makers or to aircraft makers.
Okay,
I think it will be fair. Yeah.
thank you.
Hi, this is Alon from eVTOL.com. Just wanted to confirm that this new MEA, is that the technology that's going to be on the fuel cells that you're going to be delivering to Piasecki and offering to the market in conjunction with Piasecki?
Yes. So, but actually, this is one of our plans. But what I would like to emphasize that existing technologies based on membrane electrode assembly, which we have from BASF, it's more than enough to build the system based on Piasecki needs. But of course, we have a plan to switch in a couple of years, man. As soon as we will build that MEA, switch all our range of product to that membrane electrode assembly and build fuel cells based on that new technology.
Okay. So what's your timeline for delivering those first systems over to Piasecki, and when are you expecting to make the switch to the new assembly? So
our agreement with Piasecki covers 5 systems. So 650 kilowatt system, which we have to deliver up to 2020, middle of 2025. And that's 5 sets, include also a certification process. So the first system for demo flight should be delivered in the middle of 2023 with 4, for demo. But I would like to emphasize that in that agreement, it's not only just a one system. So this is a multi-stage cooperation, which not only includes just a demonstrator or a ground test, but also for certification process.
Okay, great. And so, compared to your existing technology, with this new technology, for the Piasecki application or similar eVTOL applications, how much? I mean, do you expect the size of the stack to shrink, or do you expect that the developers will use the extra power?
Exactly. So again, depends on what customer needs. So what is specific power? It's the weight of the system. So let's imagine that you have, for instance, let's say 650 kilowatt system, right? And the weight of the system in 2 kilowatts per kilogram will give you about 300 kilograms, right? So it means that if you have 3 kilowatts per kilogram system, it means that the weight might be decreased so significantly, and of course the size of the system will be decreased too. So that's 3 kilowatts per kilogram, and next level specific power bring a lot of benefits for the company, not only in terms of weight but also in terms of volume.
Okay.
Please correct me if I'm wrong.
Yeah, you're absolutely correct. So our idea, if you intensify electrochemical reaction the same volume, you just you have 2 choices: either increase power output if necessary with having the same volume, or reduce volume providing the same power output. So in proportional. So if you can generate 2 times more power, you immediately can reduce 2 times volume. Besides components that could be considered as a balance of plant, but the main volume is occupied by generating modules, generating power.
Sure. So, which option do you think would be, more attractive to Piasecki, which is obviously developing its aircraft now, assuming a certain volume, I would guess. Do you think that they're going to be, using more power, or eventually looking to decrease the volume of the system in the future?
Actually, we just finished with them an exercise, and existing technology absolutely fit their volume requirements. As I said, we did layouts and integration of the system inside their tail of the helicopter, and it works well. But of course, I think so. Piasecki, as I know, I think it's better to ask them. But as I know, they have a different platforms, and some of cases they want to increase payloads, or for some cases they want to provide more power for their aircraft, and of course decrease the volume of the system. So it depends on because they also develop the A890, as I understand. So it's just first platform. It's a platforming solution too. So further depends on different customer requirements. It might be modified for very specific needs and specific use.
Okay, great. Thanks very much.
Thank you for your questions.
Hi, this is Ken Swartz from Vertiflight magazine. A couple of questions for you. The main focus of today's announcement, just so I'm clear, is the adaptation of a BASF membrane within your fuel cell technology. Is that correct? That's the key point of today's announcement?
Not really.
Maybe I can answer
Yeah.
on this question.
Go ahead.
It's a very good question, actually. You see, as you see this picture on your screen, current HTPM technology was developed for mostly for stationary applications. This membrane is very good membrane, but membrane electrode assemblies based on the current membrane was developed for stationary applications. For air transportation, for transport applications, much more power, specific power is required, and different requirements exist for stationary and transportation. For stationary, efficiency more important. For transportation, power output, power density. And our goal, we realized that the current, especially the new membrane, can provide significant benefit for specific power, for power density. And now we found the way how to get higher power density using the same membrane, adopting it for transportation. So our task, our plan is to build absolutely new membrane electrode assembly which generates electric power around the same membrane. And the features, unique features of this membrane developed by Brian Benishevich together with BASF provides all necessary conditions, all necessary properties for this work. That's the focus. So we found that this membrane is really can meet all requirements for transportation, for air transportation, and our work to open to recover to get to this potential, to recover this potential.
So if you're a fuel cell developer and you're looking for, I guess, enabling technology that might be out there to improve your fuel cell, then you're very closely watching membrane development by various companies around the world. And this is an example of one membrane that allows you to achieve higher power levels. In other words, is there a whole industry out there developing membranes such that there will be other step changes in power based on this? I'm trying to get a bit of a context for this in terms of the fuel cell development taking place today. Does that make sense?
Maybe I did not catch everything, but I would like to say that HTPM technology was very underestimated by the date. It was how to say, it was considered as a niche technology, and nowadays we see how much developers, how much potential customers how to say, switching starting to switch their attention to HTPM, and we believe that this new technology also should how to say switch on the consequence of new implementation in all markets, not only in air transportation, all markets. So but as Alex explained, our goal is to use this best advantages of this technology, of this membrane, of our future membrane electrode assemblies for air transportation, because it perfectly meets fits all needs on air transportation. But a lot of our segments will benefit from this same technology, and we believe that the interest to HTPM technology will increase very rapidly in coming years.
Now, when I was listening to some of your earlier presentations to the Vertical Flight Society, say earlier this year when HyPoint first came on the market, at that time when you were talking about aviation applications, was it within the context of HTPM technology, or has the company actually pivoted and now has two sort of technology streams, low temperature and high temperature, or were you always talking about high temperature?
So our team is always, we are talking always about high temp, because we figure out that LTPM, how to say, we cannot achieve higher performance and higher specific power because it's a fundamental limitation of lithium, of low temp membrane. So on actually low temp membrane technology right now achieved, I would say, let's say maximum of their performance. So of course you can achieve them higher, but it will be like more. So you can have 10%, 15%, but in comparison with high temp, I would say that we are right now at the 50% of maximum performance if we will do the next membrane and etc. And Brian can confirm that. So Brian, so please add. So it's gotta say really a lot of further development and further improvement in the membrane.
Right. I mean, at this stage, as Alex said earlier, we can meet the requirements for many of the customers we're talking with, but there's a much bigger window for improvement in high temp PEM compared to low temp PEM. And so if we're going to get to what aircraft need and larger aircraft, you got to have the window above you to move into. We don't see it there for low temp PEM, and we think it's pretty obvious from our perspective that it's there for high temp PEM. And so then this joint R&D agreement is basically taking the world's leader in high temp PEM development membranes and MEAs and teaming up the two companies to develop that specifically for aviation.
Two more questions. So right now we have sort of two parallel tracks. We have the development of eVTOL aircraft, and there's aircraft that are hybrid, and those aircraft that are battery electric. Do you see your system as it matures being able to sort of plug and play and plug in to a number of these other eVTOL aircraft that are in development, or would there be major re-engineering required for, say, another manufacturer that's been focused on batteries to adopt your system?
Sorry, yeah, this is also a good question. Actually, that is covered by our collaboration with Piasecki Aircraft Corporation. The main aim of that collaboration with Piasecki is to create, how to say, main concept of the system, which will be satisfied, or let's say 90% of requirements of any eVTOL maker. But after that, so of course it should be customized based on very, very specific requirements of eVTOL platform.
Yeah, but I would like to add that not only fuel cell should be adjusted to aircraft, but also aircraft should be adjusted to fuel cell. This is
no. In general, fuel cells you don't need to be you don't need to modify. So the main idea, 10% modification will be in balance of plant, because for instance it's a balance of plant compression system. Some differences between if you would like to fly at altitude 3,000 feet, or your eVTOL will fly at 1,000 feet, or if your aircraft will fly at 10,000 feet. Depends on that. Balance of plant should be modified, of course. But fuel cell technology, which we are developing with Piasecki, I mean, based on their requirements, we do believe that we don't need to modify it.
And that would be for the engine. Would it also apply that you could put the hydrogen required within the existing airframe, substituting the space currently taken for batteries, or would you actually have to have a larger volume area to to accommodate that hydrogen in order to use a fuel cell?
Yes, some of aircraft, existing aircraft, of course, you have to modify the volume because our system has, I don't want to say greater, but yes, greater volume of in comparison with lithium measures. But it's a question of engineering. So it shouldn't be your aircraft will not be modified completely. You just don't need to provide additional volume for fuel cell. But again, when the main aim of collaboration with BASF to create a new membrane electrode assembly, which will increase specific power and system level. At the same time, it will be decreased volume parameters of the fuel cell.
Yeah, also hydrogen technologies go moving forward and will reduce volume occupied by hydrogen. So two parts of our system, not ours. So hydrogen is one part, our system is the second. Both systems, both parts will reduce their volume because it's rapidly improving both hydrogen and fuel cell, our fuel cell improving currently.
And my final question is regarding, you talked about life cycle costs, but I'm wondering, from an operating perspective, as you're flying a hydrogen fuel cell aircraft over time, and let's say you're flying 2,000 hours a year or whatever, at what point do you have to do a major maintenance or swap of a component on a fuel cell system? What's the interval and what's the cost? You know, maybe it's equivalent to a turbine engine overhaul, but once you put the aircraft in and you're flying, what's the maintenance cost or maintenance man-hour event that it will occur downstream?
So unfortunately, I don't have right now how to say that figure. So we have that definitely. If you can ask me, send me some written question, I'll be able to answer. But right now, I don't have that materials in hand. But we targeting so fuel cell. It's electrochemical reaction. We don't have any friction parts inside. So the maintenance process will be much easier in comparison with standard combustion engines or with turbine. And because, as I said, so no friction parts and etc. And yes, so modularity strategy of HyPoint fuel cell system allowed us to create like a plug and play, plug in, plug out modules.
I see. So that so that the maintenance event is relatively simple then, and inexpensive, or is there?
Absolutely much cheaper and easier in comparison with standard turbines. Yes, that's, by the way, I see at our maintenance when I drive my Toyota Mirai to Toyota, and how they do maintenance of my car. So it usually takes about an hour just to check fuel cell life, and that's it. So it's just a standard, very standard, check in the program and condition of the fuel cell. That's it.
And just one last thing in context, when it comes to high temperature fuel cells today, I'm not very knowledgeable on this marketplace. Where do we see high temperature fuel cells in operation today? Or is this an emerging technology that is going to start appearing across a number of different industries?
Yeah, Brian, can you answer please on that question?
Yeah, they have been around, as you can see from the chart in front of you, and so they've been adopted in other markets. Not aviation yet, but they have been. You know, I've got a couple of them sitting on my desk for smaller units that are for portable, and there's tens of thousands of these that have been manufactured and put into place, often for military and certain agency specifications. So, you know, to them, this is routine stuff. Now, these are much lower power. So, yeah, we're not the first to break into a commercial market with high temperature PEM. Its history has been there, and you know, you always get these early adopters for specific reasons, and then broader and broader. And you know, where we are now is just broadening that market. But you know, we believe we were the first into the aviation, and we'll probably be the ones to make it happen.
Thank you.
Mhm.
Well, I think that that will conclude our Q&A period for today. Thank you, Dave and Ken, and Ilan as well, for your questions. And thank you to Alex, Sergey, Brian, Rhonda, and Aaron for allowing us to host this webinar and your presentation. And as I said earlier, we'll get the recording out to the other members of the eVTOL Writers Group as soon as it is available, and look forward to hearing all the great postings for your news starting tomorrow.
Thank you.
Okay. Thank you very much for your questions.
Yes, thank you, Alex. Great job, Sergey, Brian, and Rhonda.
Thank you so much.
Thank you.
Bye-bye.
Thank you very much.
Yes, yeah,
Bye-bye.
well, very exciting. I'm very interested to see where we're going with this, because it's I'm with you guys. It's kind of, it has to be the future. So.
Mhm.
Thank you, Jim.